And so we're going to start with some, we'll say that x, just for some notation, is going to be x1, x2, xd. And I'll write the coordinates here in the superscript because we'll use, remember, we use the index of it to describe which data point it is. This way I can have subscripts if I want. Also, remember, this is going to be in RD. And then we're going to start by looking at these. So again, we're going to look at these linear functions. So this linear function is going to mean that it's going to be defined by these parameters alpha 0, alpha 1, x1, plus alpha 2, x2, plus alpha d, xd. Right? And if you remember, this is just alpha 0 plus alpha, this where alpha is this vector alpha 1, alpha 2, alpha d. Right? So it's just this offset plus this, so plus this dot product. So this dot product shows up again. Right? And so what's common, the notation, so I use this notation so it looks more familiar here. The common way of writing this is actually going to be g of x equals b plus, so wx. Okay, and we'll usually restrict that the w is going to be a unit vector, so its norm is 1. Okay, so it turns out we don't need to make this restriction. If w has a larger thing, we can always do this afterwards. This is kind of, there are a bunch of equivalent functions that will give this the same sign, but different values. But the sign will be the same. If I just if I divide everything through here by 7, I'm not changing the sign, because things that started positive are going to end positive. If they start negative, they're still going to be negative. So I can normalize this afterwards, but for kind of convenience, we'll think about this as being just as being a unit vector. And so this will allow this function to kind of have this nice shape to it. Okay, so let's look at the geometry of what's going on here. Okay, so we're going to have some sort of domain here, and our data is going to be a bunch of points. These are going to be the these are going to be the minus points, and then we're also going to have some plus points here. Okay, so think of, so this is going to be like, this is x1, x2, x3, x4, x5, x6, and so forth, right? And so I've drawn them differently, so the ones with the plus, with the minus sign are over here, the ones with the plus sign are going to be over here. Okay? And now the function I would like to have is going to be described by these two values, w and b. And let's say it looks like this. This means that if I want to divide them into the minus ones on this side and the plus ones on this side, so that means I'm going to have a w is going to be a vector here. It's a unit vector, so it's just pointing this direction, which means it's going to be the normal, right? So it's going to be the normal of some half space. And b is is then going to be the B. B is then going to be, this distance here is going to be B. It's the closest point on the half space to the origin. That distance is B. Okay, so if I walk through this again, if I have a data point x3, I take the dot product with W. Okay, and that puts it along this line. I'm projecting down onto this line here, right? So what happens is I projected x3 down onto here, and then I add B to it, okay? And if it's positive, it'd be over here. If it's negative, it'd be on this side of this separating line. Okay, so W gives me a normal direction, and B is an offset. Okay. And so a positive point, I project it down onto W, and I add B. So it was negative initially, but I added a positive value to it, and that allowed me to shift this line this way. Okay. Could have been I added a negative value, that would have shifted it this way, and so forth. The W was pointed in the other direction, and I subtracted B, so I put a minus sign and everything here. I would flip all the predicted labels. Okay, but this means that a linear function like this is any linear function is described in this way with these sets of these coefficients. It will give me this linear separator as well. So a linear function gives me a linear separator. Gives me, in 2D, I'm drawing a line, and on one side it's positive, on the other side it's negative. All right, so there are learning algorithms, and we'll talk about some other things kind of next week, where we do things other than functions which are defined by lines. But it turns out like most functions, well, like I don't know, times have changed somewhat, but this is a pretty powerful class of functions, and we'll talk about some kernel methods actually, and you'll see that it really kind of structurally it's going to look pretty similar, even though you're going to curve your line. All the geometry kind of are the way of thinking about mathematically is going to be the same. With like neural networks, which we'll talk about on the very last day, you'll see it's kind of be based on these linear classifiers, but combines them in kind of interesting ways. Okay. So how many of you have seen or thought of a linear classifier before? And for how many of you is this kind of a new concept? Okay, good. And again, like almost half of you did raise your hand again, so I'm kind of in the lots, but I'm guessing it's at least so it's at least fairly new, right? Another way of picturing this is if I actually looked at what the function value was, right? G is actually this function. Now what it's done is if I just look at the sign, it makes everything over here -1, everything over here +1, but it's actually this plane that comes out. If I think of the y values coming out of the plane, the range of G is a real value coming out of the plane, then it's actually this kind of half space that cuts through this plane, and it's on the positive side of the board over here, and it's on the negative side of the board over here. It's actually this linear function G, and I'm just kind of drawing this threshold, right? And this B kind of is kind of telling me what the threshold is that I'm kind of where I draw the threshold for the same function. Right? If I had it without B, then it would go through the origin right here, and I've added B so that instead of going through the origin right here, I've kind of added it up, so now the origin cuts this way. another way of thinking what's going on.
I was so like this is kind of my first time thinking about like more visually so we were doing B plus the dot product, or not the dot product, but the W and X.
The dot product. That's right.
Yeah, the dot product. What's interesting to me is that the dot product kind of changes the direction, and B kind of says how far we'll go out in that direction.
Yep.
And so that's and then that is kind of like the orthogonal plane of where we would separate out the pluses and the minuses then.
Yeah. So that's right.
Okay. That's it. Okay.
Yeah. So any way I can divide the data points by a line can be described by a function of this form. This is the form of all functions that kind of have positive points on one side of the line, negative points on the other side of the line. I guess there are some issues where, with like some divide by zeros for strictly, I guess maybe. I think that's okay here. Yeah. But yeah, so any function can be described in this way.
So this is just out of curiosity. Could you do like clustering first, and then like cluster with the positives and negatives, and then do this?
Yeah. So.
Or like, do you always assume that your data will be like all positives on one side and then negatives on the other, and then you can like.
So in this case, I'm given a label, and my goal is to try and find this line.
Right.
The goal is to find the line, and with the use case of I'm going to be given a new data point here, and I want to predict the sign here. Right? So I want to define a function I can apply anywhere in the plane and make a prediction on a new data point. So I have a new customer come in, and are they going to be profitable or not profitable? They're going to be profitable. I want to really try and kind of retain them as a customer. If they're not profitable, I can let them go, right? So the real thing is prediction of new values, right? So clustering of the data first. So I mean, there are some ways that this can interplay with clusters. So I could ignore the sign first and then try and find close-knit groups of points. And sometimes this is a useful feature to add in to try and first, so what we're going to talk about mainly is these are not going to necessarily have to have the same units because the alphas are kind of undoing the units here. So what I can do is I can assign them clusters, say k clusters, and I can add k more variables and give them a 1 if they're in the jth cluster and a 0 for all the other clusters. And this is sometimes a useful thing to do. It kind of gives a more robust feature in the process, and doing that can be helpful. But kind of, it could be that, if I moved this plus point here and this minus point here, there might be a nice clustering of points, but the line still says these are positive and these are negative, right? And so the clustering is not quite the same objective as what I'm going after. Right? So there are these different objectives for different problems, and one of the things you have to do as a data scientist is they say, well, okay, here's the data, kind of make sense of it. Do you want to make a prediction? Do you just want to find structure? And those are kind of different sorts of tasks.
So just to reiterate, people use clustering to create new features for their current, like as a predictive, like basically create a model that assigns it to a cluster, and then use that cluster as a feature in the classification algorithm. Is that what you're saying, or is that
No. So kind of like, let's say I have really high-dimensional data,
okay,
and I know there are groups of points that are kind of spatially similar to each other.
okay,
It's sometimes more robust to say, well, those points, if I don't know anything else about them, they're similar to each other in space, so they probably are going to act the same way. This is especially true if I have a bunch of data but I don't have labels on all of them. So I want to use the data I don't have labels on to tell me which points are actually similar. And that would help say, okay, there's all these points that are kind of spatially coherent up in this region, and so that there is this nice cluster. So I'm going to kind of use that as a feature, and that just sometimes helps with prediction. These are kind of some of the black magic side of machine learning more than something I can formally point to. There's a really easy to digestible reason that's foolproof why this works. It's kind of, it sometimes works, and it's some way how these different concepts fit together, but it's not really a thing where there's like a lot of a very clean, simple explanation. So it's just, but so clustering and classification are typically different tasks. Classification, you're given the labels. Clustering, you're trying to kind of add labels out of like nothing, right? Okay. So how do we find this line? So how to find W and B? So let's start with some other techniques we've talked about in class before. So we have points and we have values y, and we want to learn a function that goes to R. Kind of a natural thing to try.
Regression?
Yeah, so one thing to try is so like regression, and the idea is to transform x to this, let's say, all ones vector, and then this is x here, so now it's in Rn times d plus 1, and then I can say alpha is going to be equal to x tilde transpose, x tilde inverse, x tilde transpose y. Right, so y has -1s and +1s, right, so I can say they're -1 +1, so, and these are, I can treat them as scalar values, okay? And this gives me an alpha, this gives me a linear function exactly of this form, as I was hoping to get. And so this is okay, this gives me a solution.
I just have a quick question. So in classification, it's like a linear, we're dealing with linear models, right?
For now, next week, Wednesday, we'll go to nonlinear models, but for now.
So then, if you had like a nonlinear model for classification, then we would apply like the polynomial.
Sure. Yep. That's one of the things we'll do, but well, it turns out we won't quite use this approach or the direct gradient descent of this formulation. Kind of this.
I'm just curious about like, if there could be like other kinds of models.
Yeah. Yep. Great. Yep. So if I want to fit this with a polynomial curve, I will basically all I have to do is I can run this, but after I do a polynomial expansion of these things, and there are other ways to do as well, but that will give me a polynomial separation, and that would be when I project it back down, it'll be a polynomial separation. Yeah.
Could you, I guess, I'm having a hard time visualizing what regression would give us in this instance?
Yeah. So I was about to draw a picture that hopefully will kind of explain. And so let me draw the picture now in one dimension. Okay, and so now this is +1, this is -1. So that means that I'm going to have these data points. Let's say I've got these are all my points with the label -1, and all the points with the label +1. Let's say they look like okay, like this. Now, what is regression trying to do? It's going to try and find a line that the residuals are small. The sum of the squared residuals are small, and that line will probably go like this. Okay? I want to minimize kind of the sum of these squared distances. Right? And so this has done a reasonable job of doing that. Oh, I didn't. Okay, I drew the example slightly wrong. Okay, let's pretend I drew that differently. Okay, so let's say it gave me an answer that looked like this. Okay. Okay, and so minimizing these sum of squared distances here. Okay, and so this is doing okay. So then it means that there's some, but the threshold is now where it crosses 0. Right. So this is the line. This is going to predict -1. This is predict +1. Okay, but yeah.
Does it always go through the origin, or is that just?
No, this is the origins over here.
Oh, okay.
Right. So that this is the origin. So the offset here is B. Right. So
what's the purple plane?
the purple plane is
Where's the point that
this is where it crosses y equals 0. This is the function g. Right. So g. This is g of x. Right, and then, but the prediction is the sine of g of x.
Right.
So where it's positive is over here. These points are correctly labeled positive. These are correctly labeled negative, right? But these are labeled positive, right? When there turned out there was this other prediction I could have done, which is I drew by accident a couple times, which is right here, and this correctly labels everything. Right, so if I do linear regression, this is the optimal under the loss function I've set up, which is minimizing the sum of the squared errors. This might be the optimal choice, the red line and the purple threshold. It gives me the purple threshold, but I want the blue threshold. So it's not really optimizing the right formulation here. I'm just minimizing. If I predict this one is 1.3 instead of +1. And so it wanted to make me shift the curve further to the left because I wanted, this 0.3 was too big. But it doesn't matter, it predicted it positive, right? And this one, it said, well, the curve is actually, this point says the curve is too far to the left. Let's me move it right because it predicted -1.1 instead of -1. But that part I don't really care about. Here.
Is the goal of to change the cost function instead of evaluating residuals and like distance, y distance, is to change it to some other conception of distance?
Yes.
Or like moving.
Yeah. So we're building up to it. Great. Yeah.
So in this example, this visualization, the points are in the points are GD on here, right? But like
the points are 1D on here. This is the x-coordinate, or all the x-coordinates are captured in this exponential axis.
They need to be up or down.
And this is the function g. Before g was coming out of the plane here, now g is going up and down, so I can draw kind of the residual now.
Okay. So the z determines is on the y-axis.
The y coordinate, the y value here is now on the y-axis. Yeah. So that's a good question. So this is y and this is x. This is in RD, but I've just drawn in R1.
Okay.
Yeah. So all the x coordinates are here, and I've given them the y value as either being +1 or -1. They're only options.
Okay.
Yeah.
So that would just basically be like you pick like any x value on your x-axis and then you evaluate, take g and then you evaluate it.
Correct. And the evaluation of g gives me this line. It's a linear function. It has to be a line in this setting, and then the evaluation is the error in the prediction here, and I want to minimize the sum of these squared residuals here. There's an example in the book which I think is kind of structurally the same here, but probably actually is what minimizes the residuals. All right, so I want to kind of, the point is, yeah, we can do regression, and this is not a horrible starting point. If you saw like this example probably actually is not as bad as what I drew it, but it's not really doing the right thing. Okay, so regression is not really what we want to do. We really want to count the number of misclassifications. That's really what we're after. Okay. So what we'd really like to do is to define a function, which I'll call this g of alpha of xy, which is going to be the sum I equals 1 to n of 1 minus, this is the identity function, which is 1 if it's true and 0 if it's false. If the sine of yi is equal to the sine of g of x. Okay, so what is this doing? This is counting. This is equal to the number of misclassifications. Okay. Yeah.
Sorry, what's the symbol after the minus sign?
Yeah, so this is kind of a blackboard bold 1, or so a whiteboard bold 1, and this takes in a this.
Oh, that represents your function.
Goes from well, it goes from true, false to 0, 1, where true goes to 1 and false goes to 0. Right? So this would be called an indicator function. So it indicates if it's 1 or 2. It's binary. So if the signs match, I get 1, and if it's, which is good, so I do 1 minus that, and if they don't match, I get a 0. And 1 minus 0 is 1. So I get a penalty of 1 if they don't match, and I get a penalty of 0 if they match. No penalty. That's great. So this function is just kind of a fancy mathematical way of saying the number of misclassified points. This is counting the number of points which have the wrong sign under function g.
And we're trying to minimize.
And I'd like to minimize this. So I'd like to over alpha and r. Okay? Yeah.
I'll say that. I'm right next. That's a g of alpha. Yeah, g of alpha.
G of alpha of x. Remember, our function g had to be this linear function form, so it depends. It's a function g, but it really has these alpha parameters, which are in our d plus 1. So I really want to I fix the form of the function. I'm fixing a function class, as they call it, and I want to minimize over the choice of the alphas. Then I can evaluate this, and so I guess alpha shows up here too. Or I could say BW.
Okay.
Yeah. So, but these are the parameters I'm optimizing over, and it's a vector in our d plus 1. Okay. Okay. So now I've got the right cost function, right? I want to minimize the number of misclassified points. Seems like this seems like the right thing to be thinking about. And I've got a kind of a d-dimensional parameter space. So another thing to think about, what's the right thing to do? Can I do gradient descent. Yeah.
So yi, should we count if the label of yi equals the sine of g of xi?
Yeah, if that's true, I get a 1 here and I do 1 minus. This indicator function is kind of a common mathematical thing, so I phrase it as 1 minus indicator. I could have defined something else here and then flipped where true gave 0.
I'm thinking sine of yi, it would make more sense if it was the label of yi.
The label. Yeah, so just think of this as having a -1 or +1.
Okay.
The same thing I did here. And so typically so typically I say its values are -1 and +1.
Okay.
Sorry, yeah, I guess.
I was thinking just picture a singular.
And here again, the y's are have a +1 value
Oh,
or a -1 value,
Okay.
right? And yeah, so no, it's a good question.
I don't know if gradients have to work. Is this like the space of functions of like potential g's might not be convex? Like if you tilt b one way and if you tilt w one way, like it might lead to these humps and errors.
Yeah, so this space is the domain of alpha is convex, and it's all of our D, that's okay. But the function I want to optimize is not a convex function. Even if it wasn't convex, even worse, it does not have a gradient anywhere. There's no gradient defined here. It's combinatorial, right? I can change x or alpha a little bit, and it doesn't change the sign of g of x, right? Think of this function, or this one here. I change it a little bit, the sign of every data point stays the same. So there's like no gradient information at all. It's also not convex, right? So that's another issue, but that's kind of less of an issue as it turns out. Like most functions people build in neural nets are not convex, and things seems to work for reasons we're still understanding. But the fact it doesn't have a gradient is really the issue. Okay, and the big issue is has no gradient. It's either undefined or it's 0, and both of those things are actually useless. So I want to define a function that is going to be only 0 at the optimum, and is the gradient's only 0 at the optimum, and it's convex. So I somehow need to do that. I can't use this function. Okay, so we're kind of coming on the right track here, but we're not quite there. Yeah.
So then maybe could you there could be a way then to rewrite that function, right? So you could do 80%, or is there not?
Not that function, right? So this function, I kind of this picture is kind of messy here, but kind of think about it. This function right here, let's just adjust this b coordinate, right? At this value, it has a cost of 2. If I move it a little bit so where it crosses here, it still has a cost of 2. It still has a cost of 2. Now it has a cost of 3, cost of 4. It's a step function. This one, and this has a cost of 1, cost of 0, and I get over here, now it's 1 again and 2. So it's kind of looking, so the problem is the function in here has a minimum here, but it's this step function. Right? So it's this, so it's flat, it's flat except it's kind of stepping here. So look, there's still a minimum. It looks kind of convex, which is a good thing, right? There's kind of something convex-ish about this. The shape it doesn't look like there are local minimum someplace.
So could you then shorten, make the domain only for that specific region? And then try
Well, what I really need to do, the really big issue is not the lack of convexity, it's the lack of gradients. I need to make it so that I know if I'm here, I want to go this way and not this way. Right? Right here, I don't know which direction to go. That's the problem. Yeah.
Can you interpolate like a polynomial or not too much?
Well, so I don't actually build this function. I mean, I don't explicitly represent it. In terms of like, I never plot it, or it's going to be in high dimensions. I want something where I can just, like we did with grade descent with linear regression, I can just take the gradient of individual parts and add them up, and just kind of like close my eyes and hope it works. That's pretty much what a lot of machine learning is. So you kind of have individual, right? So we're going to have this decomposable functions, and we'll see. I'll write this out here. It's going to be decomposable again. And we're going to be able to write the gradient for each piece, and we're going to add those pieces up, and then we're going to walk in the opposite direction of the gradient. And when we stop, and we hope it's a good solution. This is what machine learning does. Okay. All right. So what we want to do is design what's called a good loss function. I've been using this term, and and basically this is going to be a proxy for this delta. This delta is actually what we want, and we're going to create some proxy for it. The proxy will be convex, and it will have a gradient. Okay? And so what we want is that this loss function is decomposable. Right? So it's going to be a function of g alpha of x, and xy are data, and I want this to look like some individual loss function on g alpha of xi y. Okay, so I'm going to want it to be decomposable, so I can look at one data point. I can get some score. This one was decomposable, right? Delta is decomposable, and I want this to be decomposable. So then I just need to define this with a function and one data point. Okay, and so in general, we'll write this as L of Zi, and Zi will be in this kind of convenient form, Yi g of alpha of xi. Oh, this is Zi. Okay, so this is kind of a really kind of cute and pretty important trick that's going on here. This Zi, if I kind of got rid of the two different cases with the signs by writing the function in this way. If g of alpha of xi is positive and yi is positive, then Zi is positive. If yi and, so let's say, let's here. So if yi g of xi okay, so if this is positive and this is positive, then Zi is positive. If these are both negative, then this is also positive. If I get a positive and a negative, I get a negative, and a negative and a positive, I get a negative, right? So because if the signs match, then they cancel. If they don't match, then I get one sign left over. So these are kind of the two good cases, and they're both positive, and the two bad cases are both negative. So now by doing this kind of trick, then I don't have two cases to deal with. So I'm just going to write the loss function, and typically loss functions are written just as the zi value. Okay?
When you say decomposable, you're just talking about you can separate out the individual losses.
That's right.
Oh, okay.
I can, this is, again, based on the premise and the idea that all the data is coming IID from some unknown distribution that we talked about a bunch of times in the class. And that means that there's some underlying kind of probabilistic model where I'm maximizing the likelihood, but because they're independent, I can take the product, and the log of the product is a sum. And think of this as the log of the likelihood. It won't always be that. It's just going to be some proxy for something, but it kind of, if I think in my head that the data points are independent examples from some unknown distribution of what the data looks like, with some positive and some negative then I should be able to decompose the total cost function as some form of sum. And hopefully this corresponds with some notion of a log likelihood. It doesn't need to, or a negative log likelihood, but this is what decomposable means. And if you believe the data points are independent, you should be able to do this. And everywhere does this.
So when we looked at the posterior, it's not a function, but we could actually relate this loss function to that.
It will kind of be like, the posterior was the likelihood times the prior, right? And so this will kind of be more like the log likelihood. Depending on if we get to it or not this lecture, we'll add another term which will act kind of like the prior. And then it will be like the log of the posterior. Okay, well, if we add a regularization term on here, which turns out is easy to do, then that's kind of like the prior. But it turns out that's a sum because again it's a product that took the log and now I add it. Right? So there's a kind of a Bayesian interpretation of all of this stuff.
That's how it's kind of goes. It's a connection between the Bayesian and
and then you want to maximize the probability of the model given the data when you can only evaluate the data on the model. Right? That's what Bayes rule allows you to do. And implicitly, you should when you see this, you think, oh yeah, independence and Bayes rule is kind of underlying this. And there are some versions of classifiers that explicitly kind of build up. There's like these, these other Bayesian ways of kind of constructing different models. We aren't going to go through that in this course. I think you'll see that in the machine learning class. Yeah. So like there's a technique called like naive Bayes, which has a different independence assumption on the coordinates, and there's kind of even as many different types of classifiers as there are clusterings, probably even more. So we're just going to kind of do some of the greatest hits here. Okay, so now we need to define this. Oh, and it's decomposable. You should think of, I have f of g of alpha of x, y is equal to the sum of f of I of alpha. So really, I'm going to be optimizing over alpha here for each of these. But the interesting thing about the loss functions are going to be as a function of the z value, right? And then there's some dot product hiding in there, and we're going to optimize over the alphas. But the way to kind of conceptualize what the loss function is to do is to look at them as a function of zi, and the alpha is kind of some parameter, right? This is actually a alpha 0 plus alpha. Right, so this is actually a dot product inside of here, or maybe this is even pushed in there, even right. Right, so this is actually kind of yi times this dot product. Right, so it's a linear function going. This is still a linear function. This is a constant here again with respect to alpha yi. So I've just kind of a zi is still a linear function, so so I can still kind of use a lot of the optimization techniques that we have been talking about before. And the gradients will still generally be pretty easy. I can do them for one coordinate, and then if I figure I do it for one coordinate, then by the linearity, I can just kind of break them out for each of the coordinates. Okay. Okay, so loss functions L of zi. Okay, so now to think about this, I'll write a bunch of these up, and so it's going to look like okay. So I'm going to have So I'm going to have this is going to be the z value here, and this is going to be the L value. Okay, of the loss. And so the first one we want to look at, this is delta. Okay, so if it's positive, I get a score of 0. If it's negative, I get a score of 1. Right, so I'm counting these classifications. This is not convex, does not have a derivative. So I want a proxy for this function. Okay, so the most common proxy is going to be called the hinge, or maybe this is the hinge loss function, right? And so this is going to be defined, L of z is going to be max of 0 and 1 minus z. Okay, so what does this look like here? It's actually kind of, yeah, so this is the hinge here. And so it's always bigger than delta, but it's going to be convex. I take any 2 points, it's always above or equal to the line. So this part is convex, this part is convex. It's got a simple derivative here. The derivative here is 0. It does not have a derivative at this 1 point. So you may have to do some case analysis. If it's, I would, generally you would just set the derivative as 0 if it's at this point. So it's not too hard to do. I've got these 2 parts to the function. Describe it as max of these 2 things. Okay, and so this says, so everything these points right here are going to be classified correctly. This is a z value of plus, say, 0.5. It's classified correctly, but it's kind of close to the boundary. So it says, let's see if I can push the boundary further away from this point. These are classified incorrectly, right? And these are classified correctly, and they're far enough away from the boundary that I'm like, yeah, I'm just going to not factor these in at all. So that's kind of what's going on. And the gradient is linear, right? So it's, z was a linear function of alpha, right? So the gradient is kind of, you have to worry about signs and stuff like that, and a case, and a kind of a condition on here, but it's pretty simple. Okay, and it's convex. Okay, so the next common one would be let's do the squared hinge. And so what this is going to be as max of 1 minus everything squared. Okay, so I've just taken the squared hinge, and now this hinge from before and I've squared it. And what happens here is now the gradient is kind of smooth here. The gradient would have been 0 here on the left side and the right-hand side. All right, so now I don't have a discontinuity in the gradient. And there are some cases where the discontinuity in the gradient is kind of becomes a problem. So this gets rid of it, but it kind of really penalizes points a lot as they become very misclassified. So this is kind of like a squared loss function, but it's, and in fact, the stuff that's in between 0 and 1, it's actually, the loss is less. So it penalizes things that are slightly classified correctly, but only slightly by less than the hinge does. But then it has more penalty if they're misclassified. Right? It goes like the squared hinge kind of goes like this. This is the squared hinge. Right, so it's this. Okay, but this can kind of be with outliers. If there's one outlier point, it can, the squared loss, there's one point I can't classify correctly. This is going to really penalize that because it's going to give it a squared term, whereas the regular hinge just had some linear penalty. So then kind of there's something kind of more in between that has both of these good properties. That's going to be called the smooth hinge. The hinge, and that's going to be that's usually all right. So let me try and write this out. It's going to be 0 if z is greater or equal to 0. It's going to be 1 minus z squared divided by 2. If z is going to be, if 0 is less than z is less than 1, right? So in this range is going to be a parabola in here, and then it's going to be 1/2 minus z if z is less than 0. Okay, so if I remember, the original delta function looked like this, right? So now it's no longer strictly greater than the original delta function here, because I've divided by half at these two spots. But out here, it's a linear penalty going forward, basically the same as the hinge, at the same rate as the hinge. I've just subtracted by, I have 1/2 here instead of 1, but it's still a linear rate going out here. And I have a quadratic rate here, so that means that the gradients match at these two spots. Yep.
Why are we using the 1 minus z for the hinge? Why not 10 minus z, or why not 3? Why is it 1?
Yeah, it's a parameter. Here, the reason for doing it here is because it's always strictly greater than delta. So you have that property. So the loss function is always strictly greater than the number of misclassified.
So this is like the translation of that specific delta function.
Yeah, these are all proxies for the delta functions, which are differentiable and convex.
So if we change that delta function to be like anything over z is equal to 5 or something, then all of these are
Well, yeah, but this really, the delta really tells me, is it misclassified or not? Misclassified, not misclassified. That's why the delta is at 0, right? This is always I drew this so you'd always know where 0 is here, and that's misclassified or not misclassified. Yeah.
I guess, why can't we take, maybe this is so too imprecise to be implemented, but we have that hinge function that just goes down like a step. Is there any way we could just interpolate it to make those corners
Okay, great. So the question is, what happens if I just do, so I have this delta function, and right, this is delta, and I make my loss function look like this, right?
Yeah, I was thinking even like the diagonal you have, you want hugging as close to the original delta as possible.
Yeah, I'll put something up that might be a little bit closer, but I mean, first, what is the problem with this function? Why is this one not used, right? I've got gradients here. This one's giving me the right value.
It's not convex.
It's not convex, right? So this one has the same optimization issues as otherwise. If I have nothing slightly classified kind of close to one side of the boundary, if all the data points lie in this regime, I have no gradient left over to work with. If all the data points are here, right, they're all misclassified correctly, I don't need a gradient, right? But these don't have gradients and it's not convex. So I can't use any of my argument. We're going to run gradient descent. If I don't have convexity, I don't really know what happens. So even in neural networks, when they use something like this inside of there, they make these convex. They want to be as close to convex as possible, even though other parts are not convex.
For the smooth hinge, from the point where it goes from 0 to, is it like 1 or a half, to the point where it actually becomes flat? Is there some advantage of having that strongly convex right there?
Well, it'll only be strongly convex if there are a full range set of points which are misclassified, right? Because then one of these by itself, it's a dot product, so it's only saying within the d-dimensional space, I have a gradient along this one direction of that dot product. But I don't have a gradient in all directions. So these by themselves in RD, if x is d-dimensional that's bigger than 1, these by themselves cannot be strongly convex. But if I have a bunch of misclassified points, they will be strongly convex. Because I kind of put them together and I get kind of a full range system. Again. So just like with linear regression, one individual loss function cannot be strongly convex. But if I have if I have a full range set of points, then those can be strongly convex. Okay, I want to put one more loss function, which is quite popular. This is delta, and then I want to put the logistic loss function, which is going to look kind of like this. Okay, so it never goes to 0. This is the logistic loss, and this is L of z is equal to natural log of 1 plus x to the negative z. This is it looks kind of bad. It's got natural log and an exponent in it. That's e to the negative z. It is differentiable everywhere. And it's going to be basically the best continuous approximation in some sense of the ReLU. So this is the ReLU, rectified linear unit, which is showing up in kind of, this is very popular so like inside neural nets, and this is just max of 0 and minus z. Okay, so I could put a shift on this if I wanted it to be better here, but this is typically how the logistic loss is written, and it gives me this kind of very smooth function that goes in kind of asymptotes with this minus z function, and it asymptotes with 0 on the different sides. It's differentiable. If you solve the function with the minus ones and plus ones with this loss function, then solving this is this to what's called logistic regression. Okay, so I can kind of, I can plug this into gradient descent. If I use this loss function, it's called logistic regression. And then if I take threshold at -1 or above 0, greater than 0, then that's logistic classification. But it kind of gives you this here. Okay, so now we have these loss functions. They're all convex and differentiable. Now I can actually, we can run gradient descent. And you can do cross-validation, and I'll talk a little bit more about that on next week. But I also want, next week, Monday we'll just talk about one simple algorithm that does not use gradient descent called the Perceptron Algorithm, which is like the simplest algorithm for finding out any sort of dot product based classifier. And that's kind of from a first principles algorithm, like, so it doesn't go through this gradient descent machinery, but it's still going to be iterative. Okay, we'll stop here.